Welcome to all of you. Now we discuss about Lagrange's equation of motion of the first kind, Advanced Mechanics, paper D.Sc. B2, semester 6, Mathematics Honors, University of Calcutta. Derive the Lagrange's equation of motion of the first kind for a particle. Consider a holonomic bilateral constraint given by GRT equal to 0. Taking time derivative of 1, we get del rg dot r dot plus del g del t equal to 0. Again taking time derivative up to this del 2g del r del t dot r dot plus dt of del g del r dot r dot plus del g del r dot r double dot plus del 2g del t square equal to 0. The constant relation 3 on the total acceleration r double dot, this term, is directly affected by the vector del g del r, as the other terms on the left hand side do not contain any r double dot explicitly. Here r dot, this r dot, only the term is this r double dot. So only the component of total acceleration r double dot parallel to the vector del g del r entered the above constant relation, this constant relation 1, because of the scalar nature of the product del g del r dot r double dot. So the constant force small f vector must be parallel to del g del r vector, that is f vector equal to lambda del g del r, where lambda is an unknown scalar. Again, considering a non-holonomic bilateral constraint of the form g r r dot t, taking time derivative, we get del g del r dot r dot plus del g del r dot dot r double dot plus del g del t equal to 0. Arguing as above, we can find f vector equal to lambda del g del r dot. Since g and r dot and g r r dot t for holonomic and for non-holonomic is given, and hence f vector are known except for lambda. Now there are 4 unknowns and 4 independent equations giving simultaneous solutions for r vector, and hence along with lambda small f vector is uniquely determined. Now Newton's equation of motion states mr double dot equal to this capital F vector A, that is the applied force, plus small f vector is the unknown constant force on the particle of mass m. Then the equation 7, for holonomic system, we can write mr double dot minus capital F A, applied force, equal to this minus small f vector for holonomic force, this equals to lambda del g del r vector. So we can write this lambda del g del r, this equals to 0. For non-holonomic system, this mr double dot minus capital F A minus lambda del g del r dot r vector, r dot vector, and t equal to 0. These are sometimes called Lagrange's equations of the first kind, and lambda is called Lagrange's undetermined multiplier. Lagrange's equations of motion of the first kind for a system of capital N particles with k constraint. Let k bilateral constants gi, rj vector, t equal to 0, I equal to 1, 2, k holonomic constants, and gi, rj vector, rj dot vector, t equal to 0, I equal to 1 to k for non-holonomic system, where j runs over all or a fraction of the particles. Then the Lagrange's equation of motion of the first kind for the jth particle having mass mj is given by mj rj double dot minus capital Fg vector A for applied force minus summation lambda I del Gi del Rj vector equal to 0 vector. I runs from 1 to k summation and j equal to 1 to up to capital N for harmonic system, and for non-harmonic system mj rj double dot minus capital Fj vector applied force minus summation I equal to 1 to k lambda I del G del Rj dot equals to 0 vector. J runs from 1 to capital N for non-harmonic system, where lambda 1, lambda 2, lambda k are the k Lagrange's multipliers, and capital Fg vector A is the total external force applied on the jth particle. Why? It has the little application in the practice. These capital N vector equations or 3n scalar equations apply to the case of holonomic or non-holonomic and scleronomic or rehonomic constraint that are expressible in the bilateral forms only. Clearly, the total number of equations is 3n plus k, as the number of dynamical equations is 3n and the number of constants equation is k. These are coupled equations, and hence obtaining a solution these equations is rather complicated. So Lagrange's equation of motion of the first kind find little application in practice, but once solved, they provide a complete solution to the dynamical problems of the most diverse nature. And this is the Lagrange's equation of motion of the first kind, these equations. Thank you for watching this video.